Oh, g'day everyone. This will either be my last or second last tutorial video, depending upon the response I get, in which I'm actually going to be covering GLMs. So, a general linear what am I doing here? A general linear model is essentially a way. It allows you to do a multitude of things, but probably the most important feature is that it allows you to combine continuous and categorical variables together in a single model. So if you think of, like, say, the stuff that you've been doing with like, say, two-way ANOVAs, and then say with a regression, obviously with a two-way ANOVA you can analyze more than one variable at the one time, which is great. And then when it comes to a regression model, depending upon the number of continuous variables you have, you're able to combine them all together. And the nice thing about being able to combine them all together is that the p-values that you get out take the other variables into consideration at a far greater strength than what an ANOVA, a two-way ANOVA, or even a regression can do. Another thing that's really nice about a GLM is that, just say for instance you went to do a two-way ANOVA, you found out that you didn't have balanced data, but maybe you had data that was pretty close to being balanced, or all the values when you did say a cross-frequency table were actually quite strong, like say all greater than 10, then a GLM allows you to analyze the interaction terms between the two. Okay, so I'm just going to pull up example from Blackboard. I'll just give me a sec. Sorry. I always get slow in. Come on. Alright. Doesn't really matter which one we choose. I will look at something maybe that has been set on general linear models. So we go to Prac 8. Okay, so let's have a look at the candle data. So we'll work with that data. We might open up a couple of data sets actually within this tutorial. Okay, where are we? Pop some. Let's see. Okay, here we are. Okay, so let's just assume for this case, so they're obvious. I think in this situation they're modeling the difference between the initial length and the end length, so how much the candle is burnt. But we'll just forget about that. I'm not going to consider. We'll consider packet as being a variable. So if we have a look at the variables that we've got here, we've got packet, color, weight, angle, initial length, and end length. Now, if we wanted to, we can really split this off into a couple of different categories. So let's just assume, I don't know what it is for this case, but let's assume that the response variable is equal to the end length. And we know this is a continuous variable, as we can clearly see. If we have a look at our other variables, in terms of the continuous variables, we've got initial length and weight. So in terms of our predictor variables, we have initial length, which again is continuous, and the weight, again a continuous variable. So these are essentially our continuous. We'll have a look at our categoricals. So our categorical is angle, color, and packet. Angle, color, and packet. So angle, packet. So all three are categorical. Now, essentially, what a GLM will allow us to do is to investigate the relationship of end length is equal to a function of the initial length, the weight, the angle, the color, and the packet. So it allows you to combine all of those variables together, which is, as I said before, really nice that you're able to combine continuous variables with categorical variables. So we're just going to go for the full GLM, and so we'll jump into that straight away. So stat, we go to ANOVA, we go to a general linear model. So the response variable is the end length, and then in terms of the model, these are where we put our variables. We're just going to put everything in. In terms of the graphs, the ones that we're looking for these two, and we want to have standardized, click OK. There are other things that we could include within this. So like within the categorical data, I haven't included any interaction terms. I just want to put all the variables in. So click OK. Okay, so the result that comes out, we see that it says analysis of variance for end length using adjusted da-da-da-da, but the key error message here is we've got rank deficiency due to empty cells, unbalanced nesting, collinearity, or undeclared covariate. So basically, what's happened here is, in the background, in terms of the mathematics that is generating this result, there is a huge set of linear equations that are being, linear and non-linear equations that are being solved. And to solve any sort of a linear system or non-linear system, there are certain conditions that have to be met. Here, these conditions haven't been met. And so, unfortunately, our initial GLM, which we threw at it, we can't evaluate it purely and solely because some of these variables are obviously causing us problems. So what I recommend to do in this case is to just reduce it down, because we've mixed continuous with categorical. Let's just change it so that we're only including our categorical variables. Now this is a good start if you haven't done any analysis of your target variable with your categorical variables. So let's just click OK, and we see that we get the same response coming up. So there's some sort of a rank deficiency. So there's something between these three variables which is causing an issue. I've got a hunch thinking it's the packet, so I'm going to get rid of that. So again, we run the GLM again. Get rid of packet. I could be wrong in saying this, we'll find out soon. No. So it was actually the packet which was causing us the errors from before. So what we can do is we can go back, we can take these output, but we can actually also just go back and do a GLM. We'll put the other variables back in. So it was initial length and weight. Then click OK. And again, we come up with a rank deficiency. So sometimes, unfortunately, with the GLMs, you've just got to play around as much as you can until you find the variables that work. There are other methods that you can use to identify it. So let's just get rid of weight as an example. Click OK, and we get results. So weight and initial length was actually weight plus the packet was proving to give us results in which we cannot compute or generate the results. Okay, so in this situation, first thing we'll do is we'll just copy all of this data. So we need to have all of that data. So remember, right-click, save lines, Microsoft Word, and then we need to send these two graphs to Microsoft Word. Okay. All right. So in this situation, we see that we've got three p-values. Now these three p-values all refer to the three different types of analysis that has been performed. So we've got end length versus color, end length versus angle, end length versus initial length. So we're trying to analyze if each of those have an impact upon the response variable with it, which is H0. So as a situation, we've got, this would be something that you would do normally. As we've got three variables that we're looking at, we need to have three sets of three sets of null and alternative hypotheses. So the first one is, if we have a look at color, color is obviously categorical, so we're doing a categorical versus a continuous here. So that just means that the mean end length size is not affected. The mean end length size for different colors is the same, and then basically the alternative hypothesis is that the mean end length is different. Different for different colours. I know I haven't worded that very well, but that's essentially what you're doing. So you would go through and you would do H0 H0 and H0 and H1 for the other two. So we've got one for the angle and one for the initial length. So in terms of what is required in terms of the output, or what you need to talk about in order to get full marks. Okay, firstly, obviously, so you talk about why you're going to be doing a GLM. You then put forward the hypothesis that you're going to be testing within this, i.e., so the mean and length. So this is for color. Then you would have, sorry to repeat myself, one for angle and then one for initial length. So the first thing you need to do is you need to discuss the p-values for each, and what hypothesis you will be accepting. So if we take the first one as an example, so the color is, we've got a p-value of 0.00, so as the p-value, or should I say, probably better worded as the p-value of 0.000 is actually p-value which is actually less than that, indicates we have very strong evidence to reject the null hypothesis. Therefore, the mean end length is affected by the color of the candle after averaging out across. So the other two variables we're looking at is angle and initial length. So you would obviously have to do the same sort of thing for each of the p-values. The next thing that you need to discuss is we need to talk about the R squared and the R squared adjusted. So this should be a fairly familiar recipe for those that have been working with, say, regression models, and those that have been working with ANOVAs, two-way ANOVAs. So in this situation here, the R squared is 54.13%, the R squared adjusted. I'm not going to bother writing out what that means. If you look at the other videos, I go into detail about how to interpret those values. The next thing that you might want to include, but this would be a very short sentence because I haven't really seen it much in the tubes, is these R and X values. So these R values just represent really large residuals. So we have plots of all the residuals here, and these are all the nice standardized residuals, and you'll notice that the main majority of them are between -2 and 2. So that's a standardized residual between -2 and 2 is a fairly okay residual, so to speak. So it's not the variance between the actual model and the observed data isn't that terrible if it's between -2 and 2. If it goes beyond that, they become extreme values, and so that's what we see in this list here, is a listing of all those residual values which have gone, in this case, less than -2, but it could have also been greater than +2. We also have a couple of these X values. Now these X values, as it says here, denotes an observation whose X value gives it a large leverage. So these are values which are really having a pretty significant impact on the results that we're getting. And so they flag them as being possible, well, just basically, they call them just X values. I don't know what X actually stands for there, but basically these are values that you might want to have a look at. You might want to, look over to make sure that they are actually valid data. It could be a way of actually identifying outliers, but the basic rule of thumb is you can have 5% of your data being R values, and the same rule applies for X values as well. So remember, please don't confuse this R value with this R squared, completely different. This just refers to large standardized residual values. So in this situation, we've only got 1, 2, 3, 4. Let's have a look at how much data there is. So if we just scroll, I'll just do a quick scroll down to the bottom. So they've got 96, so roughly, let's just make it 100. So roughly, obviously, 5% of 100 is 5. So they've got 1, 2, 3, 4. So then you would just include a short sentence saying that we've observed 4 R values. This is not of great concern, as we are allowed to have 5% of the data producing values. So just something, look, you don't have to use that wording by any means, you could word it a hell of a lot better, it just has to be words to that effect. Okay, so as I said, you discuss all the p-values, you discuss the r-squared adjusted, you then talk about these r and these x values. The next thing that you need to talk about is these two plots, and the way that you go about analysing these two plots is exactly the same as what you would do for what was I going to say? For an ANOVA, two-way ANOVA, and a regression. So what we want to see within this standardized residual is if there is no other effective variables or there's no other variable activity, we should see what we're seeing here, which is a really scattered sort of distribution. There's no identifiable pattern that exists within the residuals. The second thing that we need to look at, or the second graph that we need to have a look at, is this normal probability plot. As I've said in the other videos, this blue line represents a perfect normal distribution, and these dots represent what we've got. So as you can see here, there sort of seems to be two problems here. First and foremost, obviously a lot of the dots are actually away from the line, and therefore the assumption of the normality of residuals probably isn't upheld. And we can see here that there isn't a great deal of data as well. So what you often find is if you've got a fairly robust variable that you're measuring, the more data that you collect, the more robust your histogram becomes. So this sort of like it sort of looks like it's, you know, snaking up and down between the blue line, which is, as I said before, the perfect line. This is a result of just insufficient data. If you collect more and more data, you would actually find that this chunk would become a lot more solid. But either way, even within that, I wouldn't say in this situation that the normal probability plot needs to be done. Or should I say the normal probability plot has been satisfied, i.e. that the residuals are normally distributed. But you know, that's just something that you need to take into consideration. As I mentioned in the other videos, it doesn't mean that the results that we've got are incorrect. It just means that we cannot be confident. So you need to be aware of that, and you need to express that when you're actually doing the final conclusion of the test. Okay, now for those of you who have done this test on your data, we can see that the three p-values that we've got here are quite small. So they're all, in terms of all of these variables, they are statistically significant. But let's just say you came up with a couple of p-values that were like 0.34 or whatever, some sort of a large p-value. The method that's actually taken with a GLM is that you identify those variables. So you do everything that we've just done. So you go through, run the test, write up about all of these, and then right at the end, you know, when you're sort of discussing the confidence in it, you say, well, because these, you know, this variable or that variable or a multitude of variables has shown to be statistically insignificant, we are going to remove them from the model and rerun it. And so what I mean is, let's just say hypothetically that the initial length p-value was, say, 0.14, so it's quite large. What you would do then, so after you've written up everything again, is, as I said, you say you're going to rerun the model. So again, we go stat ANOVA GLM, and we'll just get rid of, as I said, let's just make up, or hypothetically impose that initial length was not statistically significant. Right, and so then you would have a different set of results. You would have to copy and paste those all over, and you would have to write up about that. You'll notice that the p-values have actually changed. Now, the reason why the p-values for the two variables that we've got have changed is because these p-values are actually taking into account the other variables in the model. Now, that's very different to, say, an ANOVA, or say a regression where you're only dealing with one variable. In, say, just a one-way ANOVA where you're comparing a continuous against a categorical, not that it doesn't take the other variables into account, it does to a very slight extent, but the GLM really takes them all into account. So that's why when we remove one, we can see that they have actually shifted and they've changed. So of the r-squared value, we've actually got less confidence because we actually had a statistically significant. Now you may find that, like, you do this and then you you find that you've got more p-values which are greater than whatever p-value of the p-range spectrum that you're comfortable with, and so you may have to iterate this 4 or 5 times or however many times until you get a model that is working perfectly. Now, for some of you, it may actually come up that you find that all of your variables are not statistically significant. Now, if you have that situation, what I reckon, first of all, that's not a bad thing. If the results say that they're all statistically insignificant with respect to whatever response variable you're working with, they are the results. It's as simple as that. But let's just say we had 4 or 5 in our initial model, and you may have 10, depending upon what you're doing. look at the ones that are very close to being, or as closer to being statistically significant. So say you had 0.15, 15% sort of a thing, and it's like, well, it is greater than, the 0.1 cutoff that I'm imposing on this, but compared to the other variables, let's just say they were like 0.8 or 0.9, it's actually working pretty well, or a lot better than the other ones. In that case, then you may want to rerun it with those variables which are very close in terms of the cutoff with a p-value. That would be my recommendation. So they're the main things that you really need to know when you're doing a GLN. Probably the only other thing that you need to know is that you are able to test interaction. So I have no idea whether or not the data is balanced in this case. So I'm just going to test it, like let's just take angle and color, for example. So you go to tables, cross tabulation chi-squared, and I'm just going to do a frequency table against the two. So it was angle and color, it doesn't matter what you put in for rows or columns. Okay, alright, so we see here we don't have balanced data. So we've got 18 for all of the 90s and we've got 6 for all of the blues. Now if we were to run a two-way ANOVA on this, it would come up with, so if I put in the response is end length and the row factors, so angle and color, it'll come up saying error unbalanced design. So that's because of this. Now, so we can't test whether or not there's an interaction term. We can't test the interaction using a two-way ANOVA between angle and color using a two-way ANOVA. So what the GLM allows us to do is to actually test that term. Not always. It depends upon how well the data is structured. So we'll do a GLM, and we're going to include, we'll do color, and when you want to do an interaction, you just have the multiplicative sign, so the star sign in between, so color times by angle. So now we're testing not only color and angle, we're testing the interaction of color and angle. It may come up saying cannot be done, but it might allow us to do that. So we click OK, and that's beautiful. So it has actually allowed us to do that. So we see here, we've got a p-value of 0 for the color, we've got a p-value of 0.02, which is a good value for the angle, but then for the interaction term, we've got something which is relatively high. It's not massively high, but it's relatively high. Now, you may want to, like what I would recommend, say when you're doing your initial GLM, unless you've completely ruled out any sort of interaction, is you want to put in as many different variables as you can in order to evaluate. So like in terms of our categoricals, we did an interaction between angle and color. We did find the packet was useless, but then, okay, so if we were doing this from the beginning, what we would probably want to include in this model is the weight and the initial length. Now I know weight was causing a problem before, but when you've included this interaction term, it might be alright. So we'll just try that, and then that will be as far as we need to go here. So we'll put in weight and initial length, okay, and unfortunately it comes up with that result. So we'll rerun it again, and I'll get rid of the weight, because as I said before, we were playing around, we noticed that the weight was actually causing problems. So that would be, realistically, this would be your initial model. So what we did here, this would be something, this should be replaced with the results that we're getting here. The exact same way of analysing it, the way of analysing it is exactly the same. Nothing changes in terms of how you interpret it. It's just in this situation here, we're now including all of these variables. And one thing that I'm very happy to see is that the interaction term has actually become statistically significant when I include the initial length. So if we scroll up from before, we did one where it came up and said that it couldn't do it. If we have a look at this, is when we're just doing color, angle, and color, and the interaction of color and angle, and this was statistically insignificant. Now when we include the other variable, it does become statistically significant. So that's why it's always good to, unfortunately there's no absolute way of approaching these situations. The best thing that you can do is, when you start off, is to put in every variable that you've got, and then every interaction situation that you want to put in. We only have one in this case, color, time, angle. If you have more than 2 categorical variables, obviously you'll have more interactions that you'll want to be including as well. And sometimes, unfortunately, you just have to play the game of trying to identify which term is actually causing you problems. And so generally the easiest way to do it is just to, do it one by one and see which one actually ends up causing the problem. Okay, so I hope that is okay. Just trying to think of anything else. No, I think that's pretty much covered everything. I probably won't I probably actually will do up another video on Sunday, but I'm more than happy to answer any questions that you've got. Please just post them on the Facebook page, and I'll sort of have a look at the Facebook page, once, maybe like 2 or 3 times a day, and I'll answer as many questions as I can. So good luck with the rest of it. As I said, please comment and let me know what you think, and yeah, I'll talk to you later.